So folks, we're continuing our discussion of finding inverse functions, and let's return to that original picture. This picture really is worth 1,000 words as far as everything we do with functions when finding their inverse. So if I have this function here, f, you'll notice that it is a one-to-one function, meaning there are no output values that have multiple inputs into them. This is a one-to-one function, and so it's possible for me to construct the inverse. And the way we construct the inverse is we make the output values the new input values and then map them to their original pairing. This is precisely the steps that I laid out for you in the last video, where I said, okay, if we want to find an inverse function, first of all, not all functions have inverses, so you need to confirm this one-to-one. If not, you may want to restrict yourself to a one-to-one interval. You're going to swap out the x or replace f of x with y. That's just a notational issue. Then you're going to swap x and y. This has the effect, when you do the construction, this has the effect of interchanging the domain and range like we saw in that picture just a moment ago. Then you solve the resulting equation for y, and then you replace it with f. So let's go ahead and finish this out. So here I ask you in number 17, is it possible to find the inverse of this function here? And the answer is no. F, or in this case m of x, is not one-to-one. What's different here? Here again I have the same rule of assignment. N of x takes a number and squares it, just like m of x did. These are the same rules, but notice this has a restricted domain. So if I were to look at the graph of this original function, the graph of this original function was this non-one-to-one function. But now that I've restricted myself to an interval for which the function is one-to-one, we can now construct an inverse. So let's go ahead and do so. So our strategy was, okay, we've got n of x is equal to x squared. We said, okay, call that y. And then the inverse step is to go ahead and swap the x and y. So to find f inverse, I think this is n inverse, not m. To find n inverse of x, what we're going to do is swap the x and y. So we end up with x is equal to y squared. Then in this case, I'm going to apply something called the square root method, where I'm going to say then if x is equal to y squared, y would be equal to plus or minus the square root of x. And here we can see the problem, and this is why the original function is not invertible, because in either case I would have done this sequence of steps and I would arrive here. Hopefully you see that this expression right here is not a function. Okay? If you were to go look at the graph of what I've just spelled out for you, we've got a plus or minus. If I do the plus function in red, this would be the plus function with the positive root in in blue here, and if I did the negative function in green, this would be the minus function. And this graph, is what we're claiming is the inverse, does not pass the vertical line test. So y equals plus or minus x cannot be the inverse function because it's not even a function. Its graph fails the vertical line test. So what are we going to do? Well, we get to make an extra conclusion that we couldn't make in this situation here. If I look at my original function here, we said that the x values always had to be positive. So we said originally, that should be in a different color, we said originally the x values need to be greater than or equal to 0. When we swap x and y for the inverse, that tells us the y values have to be greater than or equal to 0. And so even though this expression, when we solve it formally, we had if x is equal to y squared, then y is equal to plus or minus the square root of x. Because of this domain range flip-flop that we do with a function and its inverse, then we know that we need to take the positive root here. We know the y values have to be positive, and so I want this just to be y equals positive the square root of x. You don't need to write that plus sign, but I'm just doing it for this illustration. So now we can give that as our name of the inverse. So our inverse function, f inverse of x, excuse me, this is an f because it's n inverse of x is just equal to the square root of x. And that's our answer to this problem. So while the function m of x equals x squared does not have an inverse, if I restrict myself to a certain one-to-one interval, it's possible to construct the inverse function. Folks, a quick word on notation. You may think f inverse of x is equal to 1 over f of x, but that is not true. If you thought that, I commiserate with you. I agree with you. Because in math, sometimes we just run out of places to put symbols. And so we start reusing symbols. You probably remember that if I were to write something like 5 to the negative 1, that does equal 1 over 5. Or if I were to write x to the negative 1, that does equal 1 over x. But here I'm telling you that if we were to take f to the negative 1 of x, that does not equal 1 over f of x. It equals f inverse. So here this stands for the multiplicative reciprocal, whereas here this stands for the inverse function. And so the minus 1, meaning the reciprocal, means something different than it means right here. There's a connection between those two symbols, which is why it sort of makes sense to use them in that same spot, but they do not mean the same thing, and that can cause a lot of confusion. So I just want to reiterate, or I just want to say that if we wanted to talk about 1 over f of x, the way we would write that is as f of x to the minus 1 power, and I would put it in brackets like this. Okay. So folks, that's kind of a specialized discussion here. The point that I just want to make is that sometimes students think that if I write f to the minus 1 of x, that means 1 over f of x, and it does not, because I don't read this as f to the minus 1 power. I read this as the inverse function of f. So it means something, while connected, it does mean something different. Okay, we have 2 more things to say here. The next thing is that this pre-work assignment is not going to discuss the important topic of domains and ranges for functions and their inverses any further than we already have. But there's more to say about that, and we will see that in our in-class notes. Finally, the last topic is, and this is why we had to introduce the idea of composition of functions prior to doing this topic, is that the real way to check whether or not two functions are inverse of each other are to compose them. There's that word composition. You take the composition of the two functions, and if you get the identity function x, regardless of the way you do the composition, then you know that they are inverses of one another. So here I've got this function k of x and this function L of x, and I'm asking you, are they inverses of one another? Well, to answer the question, what we can do is we can take their composition. So if I were to take their composition, remember we learned this last time, or reviewed this last time, that would be the same thing as k of L of x. And that means the same thing as taking this function here. Let me, I'm going to color code this here just to help us out. Let's make this a red L. And so this is k of L of x. And so we take our function k of x, which is the natural log of something. Let me give myself enough room here. The natural log of something minus 3 plus 2. So we take our independent variable and place it right there. If it were x, we'd place an x, but when we do composition, we're going to replace the independent variable of that outer function with that inner function, L of x. So this would be e to the x minus 2 plus 3. So we're doing this function composition here. Folks, I have that's a typo. That should be plus 3 like so. So now if I simplify this, we end up with the natural log of, here I'll stop trying to color code it, e to the x minus 2, the plus 3 and the minus 3, those add out, plus 2. And then we have many ways we could talk about this, but maybe the easiest way is to say that there's an identity property that says if we take the natural log of e to a power, we just get that power. So this gives me x minus 2 plus 2. And when I finished doing the composition, where I took k composed with L of x, I ended up with what? The identity function. What I'd like you to do is I'm going to have you pause the video, and I'd like you to try the composition the other way. Notice that I've switched the direction. Here we're doing k composed of L. I want you to do L composed of k, and I fixed that for your notes, folks. That should be a lowercase x there. Okay. So I want you to check that. So pause the video and give that a shot. So hopefully you found that, again, the composition came out to be x. So what we've shown is I showed that, let's see, which one did I show? I showed that k composed with L of x is x. Hopefully you've just shown that L composed of k of x is also x. And so then we can conclude that these two functions are inverses of each other. All right, folks, that wraps up this pre-work. I hope this was insightful. I will be continuing this topic of inverse functions throughout the course. We're going to do inverse functions several times over the semester. And so I wanted to make sure we were all on the same page with it. If you have any questions about this, please let me know. And otherwise, I'll see you either in the next pre-work or I'll see you in class. Take care.